Yes. Okay, a background for people who need to catch up, some of which will be recorded for people who want to catch up elsewhere. Congratulations on being honest enough to want to come to this. It's a great pleasure to see you. We're going to do this because we anticipated it would be a fairly small audience, and we were going to make it moderately intimate. So at any point, put up your hand to ask a question. Also, we're going to be choosing our slides live. So rather than just go through a preordained slideshow, Pete and I will pick from the slides. I should say, Dr. Peter Irvine is an associate professor, an associate researcher. What is your?
I'm a research assistant.
A research assistant at the University of Chicago Climate Engineering Initiative, or whatever it's called. He is also a principal at SRM 360, which seeks to facilitate discussions among experts and non-experts, especially non-experts in solar geoengineering. That about right?
That's in the right ballpark, yes.
Okay, you can say it.
Yes, I'm at the Climate Systems Engineering Initiative at Chicago, and I am the co-founder and editorial director of SRM 360. Our tagline is along the lines of, we support an informed discussion. We're supporting an informed discussion of sunlight reflection methods.
Because you can find uninformed discussions much more easily.
Yes.
And SRM 360 is in the process of launching itself more publicly, yes?
That is correct. We have, for the Sharp-Eyed, we've already been online and already kind of launched, but we are officially launching here at Degrees tomorrow with exciting new data tools, including a funding data set. So where's the money come from? Where's it going? Find out tomorrow.
Okay, well, and as if you only wanted the money part of the talk, then please have a nap. So we thought we'd go through this in a few sort of like headline senses. I'm going to start off a bit more, and Pete's going to come in as the technicalities mount up. But the first question is, what is solar geoengineering? I'm not going to get into the details of the arguments about what to call different things, but I am going to take you back to 1970 and to actually the end of 1969 and to the planet Mars. The first Earth-based spacecraft goes to Mars, Mariner 9, and as it gets close to Mars, it sees that there is nothing to be seen of the Martian surface. There is a global dust storm all around Mars, and that dust storm reflects away sunlight. And Mariner 9, when it goes into orbit, this is obviously a bit of a worry for all the scientists, because they were really kind of counting on seeing what the planet looked like, not just seeing a homogeneous ball of dust. But when they go into orbit, they find that their infrared sensors can see through the dust and see the temperature on the surface. And as the dust storm starts to settle and the dust falls out of the atmosphere, the surface starts to warm up. And one of the scientists involved, Brian Toon, says this is the first time we have actually seen climate change on any planet in real time. And solar geoengineering, at its most basic level, is trying to recapture that sort of effect by putting something bright and reflective into the atmosphere. You cool down the surface. If the bright reflective stuff falls out of the atmosphere, the surface warms back up. Now, in 1970, no one's really talking very much about greenhouse gas global warming. And in fact, during the 1970s, there is quite a heated debate about the question of whether the Earth is going to be cooled down by pollution in the lower atmosphere or warmed up by the greenhouse effect, by increasing carbon dioxide emissions. As it turns out, both of those things happen. The Earth is cooled down by sulfates in the lower atmosphere, but it is also warmed up considerably more by the greenhouse effect. And this becomes very obvious when Mount Pinatubo in the Philippines erupts in 1991, and you see subsequently, especially if you take out other sort of like local noise, you see a very stark drop in global temperatures for the time that there's a cloud of particles from the volcano in the atmosphere. Do we have a volcano particles?
We do. We have something to that effect.
Almost certainly, yeah. Oh, there we go.
Whoa, look at this.
So yeah, there you see before the 1960 cooling because of Mount Agung is noticeable, but was not particularly remarked at the time. But Pinatubo really does what's what I'm looking for? Move the needle. And also, it's not just that this is important as a sort of like proof of concept for solar geoengineering, it's also important because it's actually the first time that climate models can be said to have got something right. The climate model, when before the eruption of Mount Pinatubo, people, and notably the research group around James Hansen in New York at Columbia and at NASA, that group has actually modeled what happens if you get less sunlight in because there are particles in the stratosphere, and they got an answer that was pretty like the answer that the thing that actually happened. And it's very hard to test climate models, and that's really the first. That's an important result, not just in terms of solar geoengineering, but in terms of why we trust climate models.
I might add a little.
Yeah,
here.
of course.
So I guess this would be animated, so it's a little overlaid at the moment. But these eruptions happened in single locations in the tropics, yet they produced this global consequence. And there's only certain eruptions. There's 3 here that are notable, but obviously there was lots of others. Mount St. Helens, many, many, many more eruptions happen. But crucially, most eruptions are in the lower atmosphere. We technically call that the troposphere. This is the layer with the clouds, the weather. This is where we are at the bottom of. Anything that gets emitted here, pollution from air pollution, which creates little particles, smaller eruptions, creates a cooling effect, but one which only lasts for a few days because it's quite quickly drawn into clouds and rained out. But these very explosive eruptions pierce through and reach to this higher altitude, the stratosphere, a stable layer of the atmosphere above this more turbulent layer. And there's strong circulation patterns that whip things around east-west. So a single eruption in the tropics will very quickly spread out all the way around the tropics within a few weeks. And then there's a general tendency to take that cloud and push it to both poles, out of the equator, across the planet. And so as a result, a single eruption in a single location that's explosive enough can produce this global haze that'll persist for a couple of years, which is why you see this highlight for only a couple of years, and then it slowly falls out again. So only certain eruptions produce this effect, but it's something that we could leverage with aircraft here if we can get them up high enough.
And I think also we should say at this point, it's often said that this is an effect of volcanic dust. That's not quite right. Tell us about the aerosols, Uncle Pete.
Yeah, so the volcanoes emit a lot of different things, CO2, so in the long term they have a warming effect. That's part of why the climate has changed on the very, very long term in the past. They emit dust and ash that some of us have experienced messing with flights, but crucially they emit sulfur dioxide. Sulfur dioxide is a byproduct in fossil fuel burning as well. So coal has 1-2% sulfur in it, oil too. And as a result, when you burn these things, you don't just get CO2 and water vapor, you also get some sulfur dioxide. Now, sulfur dioxide goes on to react to form sulfuric acid. And sulfuric acid is very, very keen on forming droplets. And it spontaneously forms tiny little droplets that are about the same wavelength as light. So
they're about the size of the wavelength of light.
Yes.
Yeah.
So that's what's that? Half a micron. Some very
yeah. That sounds about right.
And I think it's worth stressing, like, if you wanted to reflect as much material, as much light as possible, I think I'm sure if anyone else likes this analogy, but I do. If you had if you had a block of salt on a dark surface, one big block, you'll only reflect a little bit of light. The dark surface is otherwise exposed. You pound that salt down into finer and finer pieces, you can spread it out farther and farther and farther. That means, like, every time you make a particle smaller, and from the same amount of stuff, you're going to reflect more light. And that works all the way down to the wavelength of light. If you get smaller than the wavelength of light, the light kind of misses it. And so it happens that sulfur dioxide by itself automatically forms particles that are exactly at this most effective reflective size. So relatively small volumes of stuff. In the case of these volcanic eruptions, Pinatubo, it's something in the 10 million tons of sulfur, produces this huge cooling effect. It dropped the temperature of the Earth by between 0.1 and 0.5 Celsius. So, I mean, 1 million tons is a lot, but it's like the most reflective power you could get because the particles spontaneously form at this precise value that is incredibly effective.
Yeah, I did a calculation based on that for a book I wrote about this. And no one's ever told me it was wrong, so I'm going to quote it. And the book's been around for 10 years now. And do we have a slide that has a picture of the Earth from space?
No.
Okay, well then you'll have to imagine.
But you do have one behind.
Whoa! It's like it is actually exactly the right picture of the Earth from space too, because those few million tons, 10 million tons or so of sulfate from Mount Pinatubo, they turn into these tiny particles, and as you know, if you have more smaller particles, you have more surface area than if you have a few large particles. And it turns out that if you look at this is the Sahara, this is the biggest, brightest desert on the planet. Pinatubo was like giving the planet another level of reflection about as big as the Sahara. It was like you're putting a Sahara-sized mirror up. And that's not a perfect mirror, but that's quite something. And so that's why solar geoengineering in this mechanism is both possible and also concerning, because it requires relatively small amounts of stuff. Just to put it in context, we were saying, 10 million tons, 20 million tons of sulfur from Mount Pinatubo. Annual emissions of carbon dioxide are in the tens of billions of tons. And so this is a very different order of magnitude of activity.
Yeah, and it's worth stressing, I mentioned Pinatubo put this stuff up for a year or two. The planet cooled by up to half a Celsius, maybe a little bit less. But if it had stayed up, if that cloud had persisted for year after year after year, we'd have had much greater cooling than half a degree Celsius. So you would probably need, I think I'm going to rough ballpark here, but if you wanted to offset 1 Celsius of global warming, which is roughly the difference between roughly where we're headed and roughly where we'd like to be, so 2.5 to 1.5 Celsius, you'd only need to reduce incoming sunlight by about 1%, and that would require somewhere in the ballpark of 5 million tons of sulfur dioxide per year. Now, you would need aircraft to do this, and we could get a little bit more into the technicalities of what that would require, but it seems eminently doable.
And it's also worth noting that the Earth already, these deserts, clouds, etc., the Earth already reflects away about 30% of the sunlight that reaches it from space. So it's not like 1% of everything. It's like it's a minor 3% increase in the amount of reflection that is already happening.
See, we already have a question.
I just wanted to know, you said that 1% it will throw back the radiation to space. How sensitive is the climate? So if you put a little bit too much up there in the stratosphere by mistake,
Yeah.
and it reflected 2%, would that mean we'd all have a winter for 365 days, or how sensitive?
Well, so this is there are quite big uncertainties about, if you injected 5 million tons, I was a little tentative about it. 5 million tons in one climate model might get you quite a bit more cooling than another climate model. And the uncertainties are in the ballpark of a factor of 2, so we might be off by half. However, we would have time to see. So one of the key things, innovations, it's not so new anymore, but the last 10 years or so, people have been doing what's a really very basic thing, but a little sophisticated, is this control feedback approach. It's exactly what you do if you go to an unfamiliar shower. The shower might be twice as responsive as your one at home, but you're not going to sit there and scorch yourself. You're going to turn it on and you're going to go, oh, that's a bit too warm. You're going to dial it back. And then, oh, that's too cold. And so you can use feedback. You can use observations to go, I thought I would have cooled the planet by half a Celsius, but I've cooled it by 0.2. That means I need to add a little bit more. And over time, you can use small adjustments as you slowly build up the amount of cooling to get on track to where you want to be. So despite uncertainties in how much cooling you get per million tons, as you see temperature evolve, you could add more or less depending on that sensitivity and arrive pretty confidently at the temperature you want, just as we do in a room, just as you do with thermostats.
Yes.
Just to follow up on that, what are the time frames that we're looking at?
Yeah, so well, climate change itself is a phenomena that is unfolding over the course of, we'll see it over decades. It'll be with us for centuries to millennia. So these, the volcanic eruptions here, you can see if you throw 10 million tons up one day, you will get a cooling the next year. So there's a timescale of response that's pretty fast, but the problem we're dealing with is a problem of decades and centuries. And so if you use this in combination with other efforts like emissions cuts and carbon dioxide removal, we're talking decades to centuries.
But also, the other aspect of time scale here, in this part of Pete's diagram, this is a fairly easy and fairly fundamental thing to remember. Stuff falls out of the troposphere, roughly speaking, in a week. If you put something into the troposphere, it will be back down on Earth, either diluted in rain or whatever, in roughly a week. Stuff stays in the stratosphere for roughly a year. And so, roughly speaking, if you put, to get the same cooling as 1 million tons there, you would have to have 50 million tons there. And something that I realize we've glossed over is sulfates in the troposphere do real harm. They are basic mechanisms of health effects of particulate emissions in the troposphere. When you read about hundreds of thousands to millions of people dying every year because of pollution in the atmosphere, that's particles in the troposphere. And so there's a really strong public health agenda for reducing that sort of that sort of pollution. As you do that, and this was something I talked about a little bit in the plenary yesterday, when you reduce that pollution, you increase the effects of warming. And you are seeing that, for instance, at the moment in India, where you are seeing there has been less warming than some models would suggest over the last 20 to 30 years. But as the atmosphere starts to clean up, the lower atmosphere, the troposphere, the 1 week atmosphere, you are likely to see that increasing. You're likely to see the health will increase, but the heat will increase too. Yeah.
Related to those health damaging particles that are in the troposphere. What are is sulfur?
Yeah.
Is one of them.
Yeah. Sulfur is most of the problem. There's also and so this is something that various people have looked at, because sulfates don't stop being a problem because sulfates in the stratosphere, the way they get out is by falling down through the troposphere, and that's a real that is a real issue. There are differences though in that in the troposphere, people tend to pollute the troposphere near where people already are, because they build factories and power plants where they are. They drive cars where they are, that sort of thing. Whereas particles from the stratosphere rain down fairly evenly, probably slightly more in polar areas than others. And so the risk for, not only is that 50 times less for the same cooling, damn, that made me look like a salesman, didn't it? 50 times less for the same cooling. It's not only 50 times less for the same cooling, but also the health effects are less per ton.
You said slightly more in the polar areas. I thought it was much more in the polar areas.
Right.
Isn't it?
Yeah, so I think it does. The distribution, it does. You mainly we put the stuff in the lower latitudes, maybe not right on the equator,
Right.
and it would tend to go towards the poles. So you'd see more of it falling out at the higher latitudes. One thing it is worth noting, though. Well, first to say, the background sulfate pollution in the lower atmosphere is around 100, or was around 100 million tons, and is
Right.
falling quite rapidly as China cleans up, as we clean up fuels. So it was 100 million tons, and we're talking, say, of adding 5 million tons. So it's a 5% of the problem. The other thing is that it would come down, when it's released in the surface, it's free in the air to be breathed in. When it's falling down from above, I think much of it gets caught up in rain, and so is rained out before you have a chance to breathe it in. Which brings us to the other issue with sulfates, which is acid rain. So sulfur forms sulfuric acid, that acidifies rain, and so back in the 70s, 80s, and so on, and still today, areas downwind of polluting locations had a lot of acid added to their rain, which meant soils and lakes became acidified, and that had big impacts locally, regionally, downwind of places that polluted. We've done a lot to clean that up in Europe, North America, and places in Asia have, as they've industrialized, had an increase in this problem. So, as I said, I think this might have less of a health impact because it comes down in rain, but you would still have that acid rain problem, though it would be more distributed, less concentrated, and there's less of it.
So I think that yes, please.
Shock.
Oh, we'll come to that. I think at the moment.
Could I just ask one? You talked about the temperature, the average temperature. What's the distribution? Is it much colder at the poles and less effective in the tropics?
So, volcanoes, single location, can go off and produce a global cloud. Now, depending on where that eruption is, you can get a cloud that is biased to one side of the planet or the other. But if we were doing this ourselves, we could choose to some extent that distribution. So, I put my aircraft here at 30 north and 30 south, which seems to be about what you'd need to get a fairly even distribution. So, because it would be a choice, you can do some things to tailor it. So it's worth stressing, this is an idea that you couldn't just create an American sulfate cloud hovering over America. This is a 2D plot. I should have explained. That's the South Pole here and the North Pole there. That's the equator. You've got no control whatsoever around the east-west. So wherever you put it, it's going to whisk around east-west and then tend to go towards the pole. So the amount of freedom you have to choose is basically how much cooling overall. Do we cool the planet a little or a lot? Do we cool the equator a bit more than the rest? Do we cool the poles a bit more, but it's not that much difference? And do we bias it to one hemisphere? We could, but that would be a very bad idea, because if you cool only one hemisphere, you'd produce all these shifts in rainfall patterns.
This isn't great. There is this band around the middle of the Earth is called the Intertropical Convergence Zone. And it's sort of like the climate version of the equator. And if you cool one hemisphere more than the other, that moves. And that makes big differences to the West African monsoon, to the South Asian monsoon. Big deal moving the ITC.
And to put it another way, it moves with the seasons. So as the planet goes through summer in the northern hemisphere, that band of rain moves up, and it's part of why we have the monsoon in the summer in the north. And then as the southern hemisphere warms up, it moves down that way. So if you only cool one hemisphere, you're going to shift it. So
and we do have evidence that the biggest or second biggest volcanic eruption of the 20th century was one that very few people have heard of, and I can't even remember the name of. So yeah, that's right. It was in the Aleutian Islands. It was up by Alaska. And you can see effects on rainfall in the Sahel and other things as a result of that, because it really did move it moved the sort of like climate equator. So by and large, I think we fairly strongly think that it would be better not to do that.
Yeah. So I think there's limited degree of control, limited degree of choice. But what choice we have is we certainly shouldn't do it in one hemisphere, I think is one of the answers we have.
That's the argument. What about the pros and cons of the Arctic cooling?
So I think there was a lot of thought that we could concentrate this over the Arctic. We just did a new study, and I think Alistair Duffy my PhD student, is presenting some of this later in the week. It might be at GeoMIT, it might be somewhere else.
I think it's here.
But basically, one of the issues is, I had the mental model that you basically put it wherever you put it, and it tends to drive towards the poles. And so you'd think you put the particles here, and they would tend to be here. That's more so than if they're here, but the problem is they also distribute southwards, and there's a lot more sun near the equator. So what he found was if you injected at 60 north, most of the cooling occurred south of where you were injected. So though the particles tend to go north, they do smear all around the northern hemisphere, and there's a lot more sun the further towards the equator you go. So it's not really possible to just cool the Arctic with this method. It would have a global consequence regardless of where you do it.
The other thing to look at here is that Peter's put these planes here. These are at the moment made up planes.
They are.
You cannot actually fly a big plane that high in the sky. There are no such planes. However, you can fly fairly big planes down at 10 kilometers near the Arctic. So you can get into the stratosphere at the Arctic. I think that's a pretty second order question at the moment, but you may hear this being discussed further on in the week.
That's the key. Existing jets, we have those, and so we could use them today if we wanted to rush towards something. So it does seem, and we're now getting some results that suggest it could work not quite as well as if you do it at high altitude, but about a third as well. So even with existing aircraft, we could cool the planet through this method if we limit it to these high latitudes. Building aircraft like this takes some work. We don't have them, but it's perfectly feasible to build high altitude jets that can reach that part of the stratosphere, but we haven't needed them to date.
Would anyone like to talk any more about this level, or would you like to hear a little bit more about other methods of solar geoengineering? And I've also got a little bit of history I'd like to share.
Can I just ask a question about this figure? Is that like from a paper, or is it just like?
I believe
That's
took
from
that.
Gavin's Twitter feed.
It seems, yes, I did take notes. Fabulous.
Gavin Schmidt, Climate of Gavin is a pretty reliable. Gavin is actually James Hansen's successor as the head of the Goddard Institute of Space Sciences, which is in the building in. It's in the building in New York where the diner is in Seinfeld. So if you need to know, that's where it actually is. Yeah. And this is made with, and Gavin's one of, I think really it's fair to say, one of the leading climate modelers in the world. This uses historic data that's been gathered by Goddard and other people, and the redder line.
They do a little correction because El Nino, the planet is a little warmer than normal, and La Nina, it's a little cooler than normal. And so these volcanoes are these one-off events, and there's a lot of noise year to year, and part of that's El Nino and La Nina, so they sort of subtracted that to make it more obvious, or hopefully
exactly.
clearer.
If you look here, that's what actually happened. That's the cooling that actually happened. That's the cooling that would have happened if it hadn't been for the fact that a large El Nino started more or less straight after Pinatubo.
But if we should say that the amount of cooling we got from Pinatubo is quite uncertain, because the world is quite difficult to...
The world is difficult to work with.
I guess the question was that we're research ethicists, so we're looking at like evidence thresholds and evidence bases, and I wondered if there's like a paper that has like a consensus view of the kind of impact that those eruptions had, so that.
Well,
I'm sure there is. I mean, I would imagine it's in. AR6 from the IPCC, but but there are various places. There might even be in one of your papers, Pete.
Well, I guess what I say, what evidence can we get from volcanoes? Just want to stress. It is a great place to get an understanding of, we put particles and sulfate into our models, and then it does stuff in the models. These volcanoes provide us a really great test bed for understanding whether our models can reproduce the dynamics of aerosols in the stratosphere and how they evolve. It is not, and the amount of cooling is another thing we can kind of get a good sense of. Did they produce such and such cooling or not? The particular regional patterns of rainfall change, it's completely useless for, or is partly useless for, because A, they're even more noisy and variable than global temperature, the regional scale, and B, the climate response to a sudden sharp cooling is very different from a slow, steady cooling. So even if you had, like Pinatubo just lasted longer, its climate response in the long term would be very different from its climate response in the short term because, there's all sorts of things, but it really messes with monsoon rainfall patterns, and that's a temporary phenomena that wouldn't happen if the cooling was slower.
Wouldn't be expected to happen.
But there are some particular dynamic effects
absolutely.
of a sudden cooling that wouldn't
But
be there for.
Since you ask about the evidence base, we've all grown up with talking about Pinatubo here because it was very important, as I say, as a founding fact about climate science as well as about solar geoengineering. More recently, and in a more difficult way, we have noticed that the rate of change of global temperature has increased since around 2015. It's very hard to explain that without looking at the changes in sulfate emissions in the lower atmosphere. Specifically, you have a huge burst of dirty coal burning, particularly dirty coal burning in China in the zeros up to the early 10s. And then, not entirely coincidentally, around the time of the Beijing Olympics, the idea of cleaning up the sulfur from that coal becomes more important in China. And so Chinese sulfur emissions drop quite strongly. And there's some reason to believe there are various fingerprinting techniques that suggest quite strongly that we've seen an aerosol-mediated warming by getting rid of aerosols.
Well, that could bring us to marine cloud brightening.
It could.
Before,
But before we get to marine
before
cloud
we
brightening,
do, please.
is there a window of opportunity that this can be used, and that will close at some point according to temperature?
What-
If we are rapidly increasing our temperature more than we expected,
So,
are we able to do this later with our
Yeah.
system starting to?
so I guess I've got a graph that shows this. I'm going to do it later, but basically the rate of warming for the planet depends on how quickly we emit CO2. And the planet will stop warming when we stop emitting CO2. We get to net zero. So now the world is probably, I think that global emissions are peaking now, and then will slowly come down over the coming decades, not centuries. So I think we're going to warm fastest now, and then slower until we hit zero, and then it stops warming. So if we wait until we've hit net zero to deploy these technologies, we will have missed the opportunity to avoid some of the risks that will come with that warming. So in a sense, if it works well and could reduce risks, the sooner the better. But the more we wait until the problem's already materialized, is already here, we'll have missed it. I don't think there's anything else. I mean, obviously, tipping points, if something happens and it crosses, the coral reefs go extinct, they've gone extinct. Yeah, so I think, my view, it's, once we eliminate CO2 emissions, the climate stopped warming. But if we want to do something to limit those risks, we've got to come in earlier. But, yeah. I don't think there's any other thresholds. Yeah.
You talk about tipping points, and that seems to be absolutely critical. Because, net zero appearing whenever. But if there are tipping points along the way, how much do we understand the tipping points? And do we roughly know when they're going to happen?
can I take this, because you have to be a responsible researcher.
Yeah.
Whereas I can be. Tipping point discourse is really difficult. That there are what would have been called technically non-linearities in climate response, that things go on and then they hit a threshold, at which point either they start feeding on themselves, they've hit some sort of point of no return where change becomes irreversible. These ideas have been around for a long time. They've been sort of like coordinated into the idea of tipping points. The actual degree to which these tipping points have global effects is, there are some that are fairly obvious. There's a circulation of water around the Africa there, down there, which is called the meridional overturning current. That is a genuine, you can see it turn on and off in the paleoclimate record in the ice ages. But how sensitive it is to anything in particular is very, very open. So tipping point, it is very hard to say that if we stop at 2 degrees of warming, we will avoid all the tipping points. That said, you can't guarantee that you will go over any of the tipping points either. The margins of error, the uncertainties are absolutely huge. Yeah. It is generally accepted, though, that the risk of some of these all of these tipping points goes up as the world gets warmer.
And I think, I will also push back a little on tipping points. I think in many respects, or in most respects, the climate responds fairly linearly. So you double the amount of CO2 you emit, you're going to warm the planet twice as much, things are going to change twice as much. But that's not in every respect. Ice is obviously a clear example where you cross 0 Celsius and it melts. So I think there's things like the ice sheets, sea ice, permafrost, where there is a sharp line where they act differently when you cross it. And I think the tipping point kind of gives you a sense of a domino, that if you touch it, it'll collapse. But many of these things, the Atlantic overturning circulation, the ice sheets, the collapse would take centuries. So it's not a instant, we're into a brand new world and it's terrible. We're pushing the Earth system into a new space, and it will evolve in ways that we may not like. And the warmer it gets, the more the world is going to change, and more dramatically. I think it's also worth stressing, on the other side, on the impact side, ice is one of those clear thresholds, but there are also thresholds in human tolerance for heat. So above a certain level, the human body can't survive. But before that, you can't work outdoors strenuously. You can't work outdoors lightly. And so that heat threshold is an important one. The similar thing with coral reefs. If they cross a temperature threshold, they expel their little symbiotic creatures, and they bleach and they die. So as I said, much of the climate system responds linearly, twice as much warming, twice as much change. But there are these thresholds out there, and I do expect that, you warm the planet twice as much. Each tenth of a degree is probably going to be greater impacts in the past. So yeah, it's a.
Yeah, I think that's fair. It's also worth pointing out that there is a community of scientists now working on tipping points who, if you were looking at this from outside, you might expect to be a community of scientists that's also interested in solar geoengineering, but that would reflect an innocence with respect to how scientists actually work. The people in the tipping points community do not talk about this very much.
No.
In fact, they actively avoid talking about it.
Yeah, they had a 500-page report which had 2 pages on solar geoengineering, and it was 2 pages to reference their own comment from 10 years ago saying we don't need to talk about this. So, yeah, it's.
So, would we like to talk a little bit about policy? Would we like to talk a little bit about marine cloud brightening? Marine cloud brightening. Okay, I'm going to pass this to Pete mostly.
So, yeah, Ollie was mentioning the cleanup in China. Cleanup in China. There's also been a cleanup over the oceans. So, as I mentioned, sulfur is a byproduct. It's an impurity in many kinds of fossil fuels, including ship fuel. And so we cleaned up a lot of oil elsewhere, but ship fuel was relatively dirty until very recently. There was a big switch where they suddenly cut down emissions of it. But before they did so, ships would leave, or ships still do leave, these tracks, these white streaks you can see through this cloud here. The sulfur pollution forms those tiny little particles that we were talking about, and those can affect clouds. So clouds made of water, with little water droplets. Those water droplets don't form spontaneously. They need to have a little seed, a little starting point. And those sulfur particles act as a little starting point. And so you can stimulate the formation of cloud droplets, and you can end up with more smaller droplets for the same amount of water in your cloud. And so the passing of these polluting ships, rather than darkening the clouds as you might expect, brightens them. And so you can see here this patch has been brightened, but across the whole ocean, down these shipping tracks, we've seen this brightening effect. And now that we've cleaned up air pollution from these ships, we're seeing that brightening effect being lost at the same time as we're seeing China cut back, and at the same time as emissions are reaching a record high for CO2. So that's part of why temperatures are surging in recent years, although exactly how big a part is unclear. So,
and it's worth saying that this switch in 2020 was due to changes in regulation by the International Maritime Organization. And they were entirely well-intentioned and possibly effective in that the modeling that they were looking at showed that even though these ships are emitting their sulfur in the high seas, the sulfur is blowing back onto the continents and is causing an estimated 40 to 70,000 deaths a year. So it wasn't a sort of like tidy-mindedness. They really do have a strong public health position. However, it is also true that people told the IMO for many years, you really ought to mention, you should think about the fact that this will unmask, exacerbate some of the greenhouse-induced warming. And the IMO showed a remarkably consistent unwillingness to engage with this subject.
Well, it's tricky stuff. I can appreciate why they didn't want to. So this is just a little graph showing, polluting ships did this and have brightened clouds. We could do that in a cleaner fashion, or scientists are thinking about doing this in a cleaner fashion. Rather than using sulfates, which have a health impact, the idea is you could take seawater and then aerosolize it. Spray out tiny little particles using something that looks like a snow fan. I'll show you in a minute. Do that, emit that up into your clouds, and for the same kind of reasons that I was describing earlier, those tiny little particles would act as the seed for a water droplets to form, and so you could have clouds forming with more smaller cloud droplets, making them more reflective and probably a little longer lived. So we could do this artificially, we could do it with sea salt, and it could have much fewer health impacts, or I'm not sure exactly the health impacts, but a lot less than sulfate, which we know to be very damaging.
No, it's more or less because salt dissolves in your lungs in a way that sulfate doesn't. So if you breathe in something
not as bad as something like sulfuric acid.
Indeed.
Yes. Okay. So here are those snowblower things. So this is one of the few field experiments that we've had in this field so far. This is from the Great Barrier Reef work at Southern Cross University. So they're worried about the Great Barrier Reef, which is very close to these temperature thresholds. And they're looking not to change the whole global climate, but to cool those reefs when it gets to those high temperature points for a few weeks. But the technology they might develop could be used more broadly. And so here they are testing one of their early sprayers, testing to see how what's in that plume, are the particles the right size? And they've gone on to do this for several years, and they're hoping to understand how the clouds up here are changed by these interventions, and seeing whether they can develop sprayers that are effective enough to generate enough particles to cool the climate. So there's this work going on in Great Barrier Reef. There was another experiment in Alameda in California that went for a couple of days before getting cancelled. And there's a couple others in the works. But yeah, this is an area where much of our understanding of this field is based on computer models. But in some respects, the only way to develop our understanding of these basic processes is through doing things in the real world to test it.
So, again, as a sort of research ethicist with a background in biomedicine, when you look at like when you look at sort of like acting ethically and all these kinds of, and building it based on your evidence base, is that like in research ethics, you have this kind of nice tool that's called the randomized controlled trial that allows you to learn, and also you're doing something, but primarily it's research because you're trying to learn something. You want to know if a drug works. You wouldn't want to prove a vaccine without it. This kind of thing, in certain contexts at least. What's interesting in the case of solar radiation management and the whole field of SRM is that it seems that, I mean, again, I read the UNEP One Atmosphere document, and it was talking about the sort of like three activities, like you've got modeling in computers, then you've got small scale sort of tests, and then sort of large scale deployment. And what I find interesting is that, like, for example, that when you can talk about an experiment, it's like it seems that there's just this natural continuum between small scale tests, which you may do for things like feasibility, and obviously you'd want to look at the impacts on sort of local weather and things like that. But like, then you also have this sort of almost like chasm on the other side, and okay, large scale deployment, and it seems like that's
There's an interesting analogy here. For many decades, in many countries, people have indulged in cloud seeding of a different sort, which is intended to make rain or snow fall in particular places or not in other places. And this endeavor has been profoundly hampered by exactly the lack of the ability to do a controlled trial. Because if you do it and it rains, you can't say, well, if I hadn't done it, it wouldn't have rained. The way forward that was chosen here is there are some sorts of cloud that form so regularly and predictably that you can actually seed, not seed, and see the difference. But also, you're now finding that there are also ways of doing it to some extent with natural experiments, because it's possible to spot things using I'm not going to say AI, but using forms of machine learning. So we were looking at the ship tracks. It was never possible for researchers to see all the millions of ship tracks and grade them all on their own. It has turned out to be possible for machine learning programs to do that. And that has allowed people to get a lot further than I think we would have expected 5 years ago in being able to say what the degree to which changes in ship emissions have changed warming. And I think it's very clear that if one got anywhere close to trying to see what actual cooling effects people were having, an event was having, machine learning would very much be part of the way you'll build that in. However, it is true there is a huge difference between the local and the global, and marine cloud brightening is very much a local to regional effect. It's much more uncertain in some ways because it depends on cloud dynamics, and clouds are complicated behavioral things. They do their own dynamical stuff. In that way, it's much more complicated than just establishing a layer of aerosols in the stratosphere. But it has the advantage that you can turn it off immediately. You don't have to do it globally, all that.
Yeah, and just on the testing, I just want to elaborate something. So it will not be possible to test how the climate would respond to these ideas, except by doing it. Because if you want to test how something changes, you have to change the thing. And the climate, one way to think about it is a 30-year average of weather. So it's not possible to test that. But what we can test, what we can do, is at these smaller scales, like what is happening in that plume? What are the particles? How large are they? What's their distribution? And then at small patches in clouds, we added the seeded particles to the clouds. How did these clouds change different from the ones next that weren't? And that understanding of the processes, the small scale processes, can then go into the cloud models that then can be built to make better projections of the long-term effects. I should say briefly on models, these are exactly the same tools we use for climate change. So climate models, the ones that help us project the consequences of climate change, are the same tools we will use, and we are using to project the effects of solar geoengineering. Though there are some parts that this might help, we need to address that aren't in them very well at the moment. But there are, so it's the same set of information tools.
And they can only be used in the sea, in the ocean, or they can be afterwards?
Basically in the sea, because over the land, there isn't a paucity of material in the air that can stimulate droplets forming. There's dust and everything all over the land, but the seas are historically, normally, quite low in providing those so-called cloud condensation nuclei. There are naturally few of them over the seas. There are naturally a lot of them over the land. So in any circumstances where clouds can form over land, they typically will. The thing that's odd about the oceans is that there are situations where there's enough water to form clouds, but no nuclei for the cloud droplets to condense on. And so that's what a system like this is doing. It's providing more nuclei.
And the ocean is a lot darker as well, so you get a lot more of an effect over the ocean.
Yes,
Yeah.
thank you. Since this is a 101 class, I will ask this question. What was the downside of this solution?
This was marine cloud brightening.
Yeah.
So marine cloud brightening does sound a lot friendlier. So stratospheric aerosol injection, we're talking about sulfuric acid in the stratosphere. We're invoking volcanoes.
This is seawater.
What's that?
This is seawater.
This
Yes.
is seawater. So I think on the face of it, it does sound a lot friendlier. I'm quite a bit more. Well, I'm quite concerned about these ideas because they're very regional in character. You can deploy marine cloud brightening. You have to deploy it at the sort of the local or regional scale and scale up. That means you can have individual nations doing it in their own neighborhood and saying, it's our business, it's none of your business that we're doing this. But also if you scale this up to try and cool the whole planet, you will cool the planet through patches. So there'll be patches of the Earth that you cool a lot more than other patches. And that will set up changes in circulation, changes in rainfall pattern that might be quite a bit more dramatic than the changes we'd get from an even aerosol cooling from stratospheric aerosol injection. So it does sound a lot friendlier. I am also pretty concerned about the regional rainfall pattern consequences of these ideas.
But if you, based on the original setup, which was deep sea shipping,
Mm-hmm.
creating these clouds,
Mm-hmm.
doesn't it sound like a very good idea just to replace? Since the ships now have cleaner fuels, if you just put one of these, you just keep the same pattern of clouds that you have had for decades.
Yeah, I mean, I haven't seen people proposing that precisely, but that could be a reason. That could be an approach.
Absolutely. I mean, if you were to create ships that emitted aerosol particles similar to sulfate particles in the same amounts as ships used to do, you could have that effect. But it's not clear that that would be the best way of using that cooling effect. That would cool the places where ships used to cool. So, for among other things, going back to something we talked about earlier, that would typically cool the northern hemisphere more than the southern hemisphere because there's a lot more shipping in the northern hemisphere. But it is the biggest problems with marine cloud brightening are it might not work very well. It's not clear that these sort of things are actually producing the particles that are optimized for reflecting away sunshine. And the other thing is, as Pete says, in order to have if you were to try and cool this conference center with with something analogous to marine cloud brightening, you'll basically have the AC on in 3 small rooms trying to cool down the entire conference center. And to get the whole conference center down by a couple of degrees would mean that those rooms would be very cold indeed.
It would spread out, but
but that's the point. You could do it, but you wouldn't want to be in the rooms that were being cooled.
Yeah.
So you'd have to cool some parts of the world a great deal to get the average effect.
and that produces big shifts in rainfall patterns, which you've seen in a lot of simulations.
Yeah.
Like you cool these big patches and you change where rain falls.
So why did California stop it?
That
I think that's probably best over coffee. But the
Sarah Doherty, if you find her,
Yeah.
can tell you more. She was on the inside of that.
But the level of permissions that they had sought was not up to the job for it. The other thing is they weren't doing it. I mean, no, they were doing it in Alameda in the Bay, and that's not a particularly good place to try and build new clouds. As you probably know, the cloud system over the Bay area is pretty well already sorted. It's not hard to get clouds over San Francisco.
Can I ask you a
Yeah.
question? Water vapor, I thought, was a greenhouse gas.
It is, yes.
So if you're shoving up water vapor, what's the
It-
deal there?
Not so much. So there is an awful lot of water vapor in the atmosphere. So this is the seawater is getting sprayed out. A small amount of water vapor that's around our salt crystals evaporates out, slightly cools the plume, but the amount we're talking is very, very tiny. So the leverage is these tiny little particles change the properties of the existing water vapor that's forming our clouds and giving you more smaller droplets that reflect light.
And the effect of the reflective effect of a drop of water that's coalesced into a droplet is far higher than the greenhouse effect of that same amount of water if it was just absorbing infrared radiation.
Yeah. Great. Well, we did a couple of the methods.
We done and I think because there's a certain amount of we should just mention for completeness. People have talked about putting mirrors in space. You can't do it at the moment on anything like the scale that would make any difference at all. Now, whether Pete talked earlier about the fact that you might think about solar geoengineering going on for centuries, and if that were the case, then you might, a century from now, with a completely different industrial infrastructure, be able to do things in space. The other thing is that there's another form of cloud intervention called cirrus thinning. People don't really fully understand it. It might have some good, it might have some advantages, but it would also have some of the disadvantages that Pete mentioned, that you kind of have to do it you have to do it locally and regionally at the places where there's cirrus cloud, and so you're a little bit stuck there. Yeah.
So again, sort of thinking slightly analogously from biomedicine, like there's often this talk about like giving treatments as like drug cocktails.
Mhm.
So I think the question of like cocktails has also been sort of posed in the SRM world. Like, do we need a bit of SAI, a bit of, how do we, what would that sort of deployment look like? That combination therapy for the planet almost. So my first question is like, is that likely to be like a kind of, imagine that we were to get this deployed, these various technologies deployed, would it look like that kind of sort of combination approach? That's my one question. And the other question is actually, can you do SAI without causing some form of cloud? Like, do you unintentionally actually, by doing one, do another?
Yeah. So stratospheric aerosol injection, as I was mentioning, would be a global intervention and could produce a fairly even global cooling. But it could not restore regional rainfall patterns. Climate change is changing regional rainfall patterns. Offsetting the warming with stratospheric aerosol injection would change rainfall patterns in a different way. They'd probably be less changed overall, but some places would see greater change. So if you wanted an even pattern of cooling, SAI can basically do that. But people have thought a bit about whether if you could add patches of marine cloud brightening here and there. But I think one of the challenges in this field is what should we want and how should we go about simulating it? So I think people have done 1 or 2 simulations, but in a sense it's a policy choice. And so we've defaulted to something simple like an even pattern of cooling being a reasonable target. But you could imagine something coming the other way. Rather than global top-down, you could imagine like the regional marine cloud brightening effort over Australia or individual nations pursuing it. But it gets very complicated, and it's a little unclear to us where we should study, where we should focus.
I think one, if you're going to do it in the medical sense, you'd probably think of stratospheric aerosols as being a systemic treatment, and marine cloud brightening as being more topical. So that, and obviously there'll be some things that go beyond my medical knowledge, gained almost entirely from watching reruns of House. But I'm sure there are cases where you want to actually treat a particular localized thing as well as the systemic thing that's causing it. We are.
Lightening, you were saying the other technique, which is the difference between
Cirrus thinning. Cirrus clouds are high up in the atmosphere and they warm the Earth, and it is plausible that by putting yet more cloud seeding droplets into those clouds, you could remove them to some extent, and that would allow more heat to escape from the Earth, and you would cool things. It's a different form of, it's much more analogous in terms of its effects to taking carbon dioxide out of the atmosphere than it is to stopping sunlight from coming in.
Except it's patchy.
Yes, I was going to say, it's
Yeah.
patchy. Pete doesn't like patchiness.
No, I'm not a fan. Well,
He's not
because I guess the biggest concern with these are the regional rainfall changes, and this one is more like CO2, which is good, but it's patchy, which means you're gonna produce changes in rainfall that might be more dramatic than you would see with an even pattern of cooling.
So
just a quick note. I think, like, roughly speaking, I'd say, I don't know, 70 to 75% of the effort in this field is on SAI. Maybe 20 to 25% is on MCB, and maybe only 5% is on cirrus cloud thinning. There's a couple of other ideas. I mean, some people looking at sunshades in space. Some people are thinking about local albedo things at the local scale, but they can only really have,
albedo, by the way, is just a word for
reflectivity.
how brightly something reflects. And it's a great shame to me that it's a technical term, because I think it's a lovely word, and I would happily see it in. Oh, look at the albedo of that car out there. It would be lovely, but that's not what people say. I think I'm going to say something a little bit about policy history, and then the other thing was we did have an earlier question which we put off about termination shock, which is naturally a good question to come to at the end of this event. But in the 1990s, in 1992, the American National Academy of Sciences put out quite an important report on greenhouse warming, and it took solar radiation management, solar geoengineering, and carbon dioxide removal quite seriously. It said there are basically three things that you can do. You can reduce emissions, and that will reduce the forcing on the climate. You can do something to offset emissions, either by sucking carbon dioxide out of the atmosphere or by one of these techniques that we've just been talking about, or you can adapt. And it said you should be looking at all three of these. However, the policy mechanisms that were created that same year in Rio at the Rio Earth Summit, where we got the UN Framework Convention on Climate Change and also the Convention on Biological Diversity, they did not look at all at those offsetting mechanisms. And in the case of the UNFCCC, it also didn't look that much at adaptation. It speaks about it, but for certainly the first 15 years or so, all the effort was put into mitigation, which in climate speak means emitting less carbon dioxide, and who should emit less carbon dioxide and who should take which burdens became the focus of climate policy, to the extent that that adaptation, which among other things applied much more in the global south and the global north, was really seriously sidelined, and all forms of geoengineering, whether through carbon dioxide removal or reflecting away sunshine, were not up for discussion. Indeed, in the way the UNFCCC is set up in the actual in the text, there's really no place within that treaty to talk about solar geoengineering. You have to really work to find clauses in the treaty that apply to that. This changed a little bit. No, this changed implicitly with the climate agreement in Paris, in which effectively the Framework Climate Convention stopped being a framework, and we actually now have the Paris Agreement, which was a big step forward. It made clear that the eventual aim was not to be not emitting at all, but to be taking as much greenhouse gas out of the atmosphere as you're putting into the atmosphere. That's where the buzz phrase of net zero comes from. And a few years later, with an IPCC report, that interplanetary intergovernmental panel on climate change, a report from the IPCC that had been called for by the Paris Agreement, showed people for the first time with sort of like charts and diagrams quite how much carbon dioxide removal was implicit in any attempts to get to keep warming to 1.5 degrees or below 2 degrees. And so at that point, so that was about 2018, carbon dioxide removal becomes something that people talk about much, much more, and it develops sort of like policy mechanisms about it. This is also because economists, including my beloved colleagues, are very keen on the idea that the proper way forward is to price carbon emissions. And if you are pricing carbon emissions, you can imagine a market for taking carbon emissions out of the atmosphere and saying, give us some money, I just took a ton of carbon dioxide out of the atmosphere. Whether that can actually work is a much more complicated story that we can go into later. But it did at least provide ways of talking about carbon dioxide removal, and it provided the context for people to start building companies about carbon dioxide removal and selling those companies to other people. Nothing like that has happened for solar geoengineering because there's not an obvious way to monetize it in the same way. And it's very hard to see how you would capture or deny people the benefits of it. So it's a different sort of thing. And as yet, I think one of the reasons why, as you'll hear in various sessions at this conference, why there is a lack of established governance is because there's a lack of perceived relevance, and that's been kind of maintained semi-deliberately by the way climate discourse has gone on. And
so I've flashed up a little diagram here. The different elements of climate policy can be sort of seen here. So this is a plot showing global temperature over time. Sort of follows historical, and then this is the purple line, sort of a relatively semi-pessimistic take of where we're going with current emissions. So red is what would happen if we just kept emitting at the same level indefinitely. The planet would just keep warming and warming and warming and warming and warming. But if we eliminate CO2 emissions, we cut them down to zero, that'll get you this purple line. The planet will stop warming, but it will not go back the way it was. You'll notice this timescale. Most climate discussions stop at 2100, which is not the end of history. Time will continue.
You don't know that yet.
No, we don't know that yet. So in this case, if we assume history does proceed beyond 2100, if you eliminate CO2 emissions, you don't put climate back the way it was. You can see the purple line is very slowly angling down. CO2 slowly filters down into the deep, deep, deep ocean. But we haven't quite warmed up to the CO2 that we've already put into the atmosphere. And those two factors basically balance. The residual warming is catching up and the CO2 is going down. And the net effect is basically no change. Which is why carbon dioxide removal has been invoked, because if you want to overshoot and get back to you need to remove CO2 actively from the atmosphere. This is an assumption of fairly large-scale carbon dioxide removal globally, something like 10 billion tons of CO2 per year, or carbon per year. I can't remember exactly our number.
CO2.
But yeah, you can see it falls, even in this case, very slowly. So this is a scenario that crosses 1.5 Celsius, peaks at about 2.5 Celsius, and in that scenario with pretty large carbon dioxide removal, we stay above that level for about 300 years. So climate change is a very long-term problem. Carbon dioxide removal can help us get out of it sustainably, but slowly and at great cost. And solar geoengineering might help us to limit warming in the meantime. This is one scenario that people look at. We call it this is overshoot, because we've gone past our temperature target. And people call this peak shaving, that you can limit the warming while we're crossing this. And
this entire diagram is known, and you can use this in conversation and seem like you've been around for a while. This is known as the napkin diagram, because the original chair of degrees, great oceanographer John Shepard, drew it on a napkin. And he used to get a little bit worried about the fact that people might put numbers on it because he thought it was very sort of like conceptual. But this is the napkin diagram. And what is more, it is also a diagram that gives you a very good way of thinking about termination shock.
Well, heavens. But before we get to termination shock, you might want to keep your eyes peeled for a napkin diagram themed napkin that will be getting distributed later.
But before you go to we can do termination shock to start it with this diagram,
Well,
because
I've got a specific
yeah,
one.
but I want
You
to use this diagram because it keeps everything. So these are your no emission cuts, emission zero, carbon dioxide removal, solar geoengineering. If you stop doing the solar geoengineering, you go pretty much directly up to that line in temperature. And you don't do it sort of like nice and slowly over decades. You do it in about 3 to 5 years. And so that means you get we're currently warming at around 0.2 degrees Celsius a decade. That would be, you could have a degree Celsius or more in a few years. So that would be a really catastrophic sort of warming. And so that, now I think, Pete, you can show your specific diagram. And I will defer to Pete on this because he and Andy Parker, who chaired this morning's session, wrote what I think is more or less the best paper on termination shocks.
So yeah, here you could see some model results that show what Ollie was describing there, this sort of sudden surge in temperature that tends towards where it would have been in the absence of solar geoengineering. So people worry that that rate of warming we'd see in those initial 5 years or so, being faster than it is here, would make it harder for societies and ecosystems to adapt.
Or indeed, impossible.
Impossible. Though, I mean, yeah, it's still going to be pretty hard to adapt to this, the climate change case. However, it's worth stressing, this is the consequence of a permanent cessation of solar geoengineering in the full knowledge of the consequences. If you were only to interrupt it, this is an interruption of 1 year. You stop solar geoengineering for 1 year and you only see a small response. As we mentioned earlier, the particles last in the stratosphere for a year or two. And so while you have some warming effect materialize, it's not much. Now, and this is worth, I mean, the world would be dependent on this technology, but the world is already dependent on many technologies. GPS, the internet, international trade. When we fly here, we're dependent on those engines on the aircraft. And in many of these systems, from failure to disaster is milliseconds to minutes before it turns out to be very bad. Here we'd have months of something goes wrong, some political crisis, months and months to put things right, to restore conditions. And I think something people often say about this is that you would be committed, if you start SRM, you'd be committed forever for fear of this termination shock. And in some sense, I showed it was a long, long time scale. We're talking hundreds of years you might be committed. If you stick to the same plan, if you stick to keeping temperatures to 1.5 Celsius, but each generation would have the choice, do we want to continue or not? And if they wanted to stop, they wouldn't have to stop like this. They could stop in a much more measured, phase-out kind of fashion. So it's a bit like a dam. If you want to get rid of a dam, you don't dynamite it whilst it's full, you drain it slowly, and then you can dismantle it carefully. But here we're talking a major commitment with these technologies.
Yeah, and I think one of the points to make here particularly is, Pete mentioned GPS and jet engines. Because of the way people think about the Earth as a system, people imagine that there might be a solar geoengineering capacity under one particular set of controls. And that's in some ways nominal. People like the idea that there would be one control system, but it's also quite unlikely. So I think the example here, rather than in actual as a mechanism of solar geoengineering, space flight is quite a useful analogy. No big nations are willing to outsource their capacity to put satellites in orbit entirely to someone else. They are not willing to outsource their ability to provide satellite positioning signals to their citizens to somebody else, and specifically also to their militaries to somebody else. So America, Europe, China, and to some extent India all have their own satellite positioning systems. They all have their own space launchers. They all have their own. Communication satellites. If we were in a world of stratospheric aerosol injection, I think it is almost inconceivable that people would say, well, it's okay for one, we'll just have one program on this. We won't have our own independent capacity on this. And that's, to my mind, one of the insurances against this sort of thing happening, because here, everyone who can do solar geoengineering has to agree to stop at the same time. And ways that might happen are kind of catastrophic and possibly beyond our scope. Otherwise, you're much more likely to see something like this, which is sort of like a bit of a change and then other people step in. If that sounds overly Pollyanna-ish, there is a linked problem, which it means no one can say how much no one can say how much solar geoengineering would be enough. You can always add more if you have the capacity to put more stuff into the stratosphere. And this means that if there are many different players who have the capacity to do this, the amount of cooling you will get will be the amount that the person with the biggest appetite for cooling wants. And that's called the free driver problem, developed by Marty Weitzman at Harvard. And it's one of, I think, the biggest issues in solar geoengineering governance. No one has any real plausible account of how you would, if you were in a world with global solar geoengineering, how you would maintain a low level, which, as Pete has shown in a number of papers, in principle can provide you with net benefits, and a higher level that might not. But for me to end off, and I'll give this back to Pete afterwards, but what Pete said just now came to me as something that comes to me as one of the most fundamental things about solar geoengineering research, which is this notion of arming the future. There's a perception that, and I think it's a true perception, that a world in which solar geoengineering is discussed and thought about is a world that probably will put less emphasis on emissions reduction. And although we all say, and we all mean, I think, that emissions reduction is crucial, we are all aware that that will be an effect, that there are lots of people out there who don't want to reduce emissions, and if this looks like a way of not reducing emissions, they will pounce on it to some extent. But if you don't do the research, people will still act like that, and in the future, people with a hotter planet will not have the information that we could have developed about how they would cool it. So this is an argument that I borrowed from a philosopher who I'm not going to name because he doesn't agree with my using it this way. But this argument is that of arming the future, preparing the future. If you don't start researching this now, you may or may not make the chances of solar geoengineering ever being used different, but you are definitely increasing the chances of it being used suddenly, badly, and in a way without a research basis.
I had a question for you, Oliver. So I think similar arguments were made around adaptation back in the 90s, that we shouldn't discuss this, we shouldn't promote this, it'll be used as an excuse for inaction. How much do you think that's affected emissions cuts, or was it all, if at all?
I think it affected the evolution of climate policy. I don't think that the policy which I associate to some extent with Al Gore of trying to suppress discussion of adaptation on the basis that it was defeatist. I think we are now in the world where emission cuts have happened to some extent, but they haven't even started bringing the curve down, let alone getting it to zero. And we spent at least 10, 15 years not discussing adaptation as much as people should have and not putting in policies for it. So if you were to go to someone like Richard Klein at the Stockholm Resilience Center, he would tell you very clearly that, the world climate policy deliberately chose to underemphasize adaptation, and as a result there is less adaptive capacity than there would be otherwise. And I think that there might be an analogy there.
What do the fossil fuel industries think about SRM?
Well, I think it's easier to say what they feel about the other form of geoengineering, carbon geoengineering. They really like that. They really like the idea that you could suck carbon dioxide back out because, among other things, the fossil fuel industry not only facilitates society's burning of fossil fuels, in doing so, it produces big holes in the Earth's crust into which you can pump carbon dioxide, and people have noticed that this is an opportunity. They do not, by and large, talk about this sort of thing because they find it frightening, and they have historically people really. I was being reminded earlier of something that I use at the beginning of my book, which is there are two different questions. There are: do you think that that climate change is a big, important problem, and do you think decarbonizing is difficult? And the only people who get drawn into conversations about solar geoengineering are people who say, yes, it's a big problem, and yes, getting rid of emissions is difficult. Historically, the fossil fuel industry has been in the, yes, getting rid of emissions is very difficult, but nah, it's not so much of a problem. If they come into the yes quadrant, then they might think about this more. And Pascal was suggesting people look at the science fiction literature around solar geoengineering, and that is indeed the plot, not the whole plot, I'm not giving it away too much, but that is the premise of a novel called Termination Shock by Neil Stephenson. It's about the fossil fuel industry stepping in to do this kind of unilaterally. I should also warn you, and this is a slight spoiler, there is no termination shock in Termination Shock. Neil just thought that it sounded like a really good name for a thriller. And when I said, you should really call this something else, and he said, yeah, but Termination Shock sounds really cool. So don't read it for a termination shock, but it's a fun book, and it has very exciting feral hogs in it. So
about 100 pages of feral hogs.
yeah,
Neil doesn't
do things by halves. There are feral hogs and martial arts competitions in the high Himalayas. But
any other questions?
I think we've used up your time.
I don't know how long does this?
Oh, we have in fact used up your time plus 4 minutes. Yes.
Oh.
Thank you for the opportunity. Just want to quick question. I just want to understand on the marine technology,
Mm-hmm.
the negative impacts that it has on the marine habitat.
I don't know how much it would. I mean, in the sense that the ocean is quite well mixed. I think it would have a cooling effect. So wherever it is being applied will be cool. But because it would use seawater to spray and would use only a small amount of seawater, it wouldn't really be adding any novel compounds or releasing any chemicals. It would just be spraying that seawater into the air. So from the ocean's point of view, no difference except for that cooling effect. So that cooling effect could have beneficial consequences. It could have negative consequences. And yeah, and I guess indirectly, as you change rainfall patterns around the world, you change river runoff. And so there'll be some effects in the same way that climate change affects the ocean by increasing river flows in some places and decreasing in others. Marine cloud brightening would do the same. But other than the local cooling, its impacts on the ocean would be quite indirect.
No, my question is actually on the marine life, the
Mm.
vibrations that it will be happening while using this technology in the sea. So the habitats, the animals that live.
Yeah, I think the amounts of water involved would be very small. So I think these would be
Yeah.
ships. So unless I hope they'd be careful not to suck up marine life as they use their sprayers. But I mean, as you saw, the sprayers they had, it was a very small mist that's coming out. It's not great volumes of water. It's relatively small volumes of water. It's about creating those very, very tiny particles. So I don't think there would be an impact from sucking up too much ocean life.
Yeah, I think that's.
I don't think you are getting the question.
Oh, sorry.
Okay.
Okay, let me phrase it this way. That technology is a big machine
Mm-hmm.
there, right there. So I'm not sure whether it's moving or it's standing still, but what it does,
Yeah.
it's spraying
Mhm.
chemicals in the atmosphere.
Seawater. Spraying seawater. Yeah.
Yes, seawater, right. And then there is a life underneath,
Mm-hmm.
and this big machine has vibrations that it makes. So and then there are
vibrations.
sharks or whatever marine life that is
Yeah.
inhabits that specific area. So what negative impact?
Yeah, sorry, I didn't quite understand. Yeah, so I think that it's a little unclear. I don't think the vision for how this would be deployed in practice has been very well developed. Whether it would be a set of floating stations or whether it would be several ships, whether it would be a few big ships or many small drones, that's all a little bit vague. But you would have to have many ships to cool these different patches. It's a sort of a small plume that would affect a few kilometers, tens of kilometers of cloud. So you need many of them. I imagine the impacts would be similar to other shipping. So fishing, I mean, obviously fishing ships do something else, but tourist ships, other things that pass through the water do have an effect on environmental life. So I think in that respect, there would be some more marine activity, more shipping activity, and that would have some impact. But I don't know the details because there hasn't been that detailed vision for how this would be deployed.
And last question.
Thank you. I only been in this space for a year and a half or so, and I'm kind of puzzled by the narrative that we use, because we are talking about the big changes that geoengineering is introducing to the world. But from what I understand, when I look at each different ideas, it's that they are not representing the change. They are kind of mimicking and trying to preserve for longer what we have today and what we know. And that is so much less scary. So if you use the example of marine cloud driving, and you introduce those seawater tornadoes on the existing burnt fleet, which travels exactly where it always travels, it makes the same clouds as it has done when it was more polluting. That is not a big change. That is keeping what we know for longer. So
I think that's true, and I think there's another sense, maybe a slightly broader sense of that, which is that people tend, when presented with thinking about solar geoengineering, they have a certain sort of like anchor bias that they compare the things they hear about in solar geoengineering with nothing happening at all. And so on that basis, almost everything looks like a worrying side effect because you're comparing it with not doing something. The correct way, or I think the best normative way of thinking about it is to compare the world with a certain amount of greenhouse warming and geoengineering, and the world with that amount of green.
So,
Has brought me here. Dennis Garrity with
Okay.
Healthy Planet
Oh, yes.
Action Coalition.
Hi.
And I have a specific question for you
Please.
about the work you're doing at the University of Chicago.
Yes.
Is that correct?
we get the slides.
Yes. You would have to email me. If you could email me at, I don't have my business cards on me.
I don't even have a business card. So, but it is.
Pete at srm360.org. Yeah, that's what it is.
So I was involved with WHO. Dennis actually called me to come to this. I'm very new to this whole topic, and that's what I love about this presentation. Dennis has been sending me for the last 2 months lots of writings and presentations and communication strategies to
Yeah.
work with WHO and Bill and Melinda Gates to do disease control priorities for the University of Washington. So every 7 years, they finance the creation of publication with peer-reviewed studies prioritizing what diseases
Yeah.
needed to be focused on.
Yeah.
So I was working with WHO in Egypt for the Embro region, and we were gathering ministers of health
Yeah.
to present the findings of the disease control priorities publication. Do you ever see anything like this happening where we can start taking this to action, or is there? And you're funding. You're funded by